All right, let's talk about one of the absolute workhorses of machine learning, logistic regression. We're going to peel back the layers and see exactly how computers learn to make those simple but, incredibly important yes or no decisions that pretty much run our digital lives. I mean, think about it for a second. Is this email spam or not? Is this tumor benign or is it malignant? These are critical yes or no decisions that happen all the time. But how? How does a computer actually make that call and do it with any kind of real confidence? Well, that is the big question we are tackling right here. Okay, so to really get our heads around this, we're going to stick with one classic example the whole way through. We're going to look at how a machine might classify a tumor. Simple question. Based on its size, is it benign or is it malignant? Now, in machine learning lingo, this is what's known as a binary classification problem. It's a fancy way of saying the answer can only be one of two things. And to keep it simple, we'll use numbers. 0 will be our no, so not malignant, and 1 will be our yes, it is malignant.
Okay, so here's what our data actually looks like. Along the bottom axis, you've got the tumor size. And see how all the dots are clustered at two levels? The blue dots down at the bottom at level 0 are the benign tumors, and the red dots up top at level 1 are the malignant ones. The whole game here is to find some kind of rule, some kind of line that can cleanly separate these two groups.
So what's the simplest thing we could possibly do here? I mean, your first instinct, my first instinct, probably everyone's first instinct is to just try and draw a straight line through the data, right? It sounds reasonable, but let's see what actually happens when we do that. Okay, so this first attempt is basically using a tool called linear regression. The logic is dead simple. You just fit the best possible straight line to all those dots. Then we can pick a cutoff point, let's say right in the middle at 0.5. If the line's value for a certain tumor size is above 0.5, we'll predict malignant. If it's below, we'll predict benign. Easy enough. And you know what? At first glance, this doesn't look half bad. See that light blue line? It cuts right through the data. And where it crosses that 0.5 mark, it creates a pretty reasonable dividing line. Looks like we've separated the blue and red dots pretty well. So problem solved, right? We can all go home?
Well, not so fast, because the real world is always a little messier than our neat little charts. So what happens if we get just one new data point? Let's say it's a very, very large tumor, but it's definitely malignant. It's what we call an outlier, way out to the right, but it's still a totally valid piece of information.
And this is where it all falls apart. Look at that. The straight line, because it's trying so hard to account for that one new point, gets yanked completely out of shape. It tilts way down. And in the process, our decision point gets dragged along with it. And now, it's getting things wrong that it had right just a second ago. This is the key takeaway. A simple straight line gets bullied around by outliers way too easily. So, okay, clearly a straight line is not the right tool for this job. We need something smarter, something more flexible. We need a function that isn't so easily fooled, one that gets that we're talking about probabilities here. Enter the hero of our story, the S-curve. And that hero has a name, this sigmoid function. You'll also hear it called the logistic function. And honestly, its superpower is beautiful in its simplicity. All it does is take any number you throw at it, positive, negative, huge, tiny, doesn't matter, and it just squishes it. So the output is always, always a value somewhere between 0 and 1. And here it is in all its glory. Just look at that elegant S shape. That is the whole secret. See how it gets really flat at the bottom, close to 0, and really flat at the top, close to 1? That's the magic right there. It means that those extreme outliers we were just talking about, they just can't drag the whole curve with them. They don't have the same leverage they had on that poor straight line. So why is this S-curve so perfect for our problem? Well, for one, that output is always between 0 and 1. And what else is always between 0 and 1? Probability. We can treat the output as the model's confidence. So an output of, say, 0.8 isn't just a number, it's the model telling us, I'm 80% sure this is malignant. That is a way more useful answer. Plus, as we saw, it's way less sensitive to those pesky outliers and gives us a really clear tipping point right around the middle. Okay, great. So we have this slick S-curve that gives us a nice probability. But at the end of the day, we still need a hard answer, right? A yes or a no. So how do we get from a probability to that final concrete decision? Well, we go back to our simple rule, but now it actually makes sense. We set the threshold at 0.5 or 50%. If the model spits out a probability that's 50% or higher, we call it a 1, malignant. If it's anything less than 50%, we call it a 0, benign. It's really that simple. It's an intuitive, clean-cut rule.
And that exact tipping point, that spot where the probability is precisely 50-50, that has a name. It's called the decision boundary. Think of it as the model's line in the sand. On one side it says no, on the other side it says yes. It's the exact spot where the prediction flips. And here's where things get really cool. This boundary isn't always just a single point. In our tumor size example, yeah, it's just 1 point on a line. But what if we had a second feature, like, say, the patient's age? Now you've got a 2D graph, and the decision boundary is a line that separates the good from the bad. Add a third feature, now the boundary is a flat plane that slices through a 3D space. And with tons of features, it's a hyperplane, which is just a mind-bending concept, but it shows you how this simple idea scales up to tackle really complex problems. And get this, it's not even stuck with straight lines. By getting a little creative with our features, we can get the model to learn non-linear boundaries. We could have it draw a circle to separate a cluster of points in the middle from everything on the outside. That kind of flexibility is a total game changer, and it's how logistic regression solves some really tricky problems. Okay, this is all fantastic, but there's a big question hanging in the air, right? How does the model actually learn where to put that S-curve? How does it figure out what the best possible boundary is? Well, any model learns by, guessing, seeing how wrong it is, and then trying to get a little less wrong. That wrongness score is called the cost. Now, with our old friend the straight line, the cost landscape looks like a nice, smooth bowl. It's super easy for an algorithm to just roll down to the very bottom to find the one best answer. But if you try to use that same measurement for our S-curve, you get this bumpy, hilly mess. An algorithm could easily roll into a small dip and get stuck, thinking it's at the bottom, when the real best answer is over the next hill. So logistic regression needs a much smarter way to measure wrongness, and the key idea is brilliant. It severely punishes the model for being confidently wrong. So imagine a tumor is actually malignant, but the model says, I'm 99% sure it's benign. The cost function will hit it with a massive penalty for that mistake. But if the model was right and said, I'm 99% sure it's malignant, the penalty is basically 0. It's all about punishing that false confidence, which forces the model to learn the right patterns. All right, so yes or no is great. We've got that covered. But the real world isn't always so simple, is it? What if you have more than 2 choices? What if you need to decide if something is, I don't know, a car, a truck, or a motorcycle? The solution is actually super clever. It's called the one versus all method. Instead of building one giant, complicated model, you just build a bunch of simple yes-no models. So you train one model that only knows how to answer the question, is this a car? You train a second one that only answers, is this a truck? And a third for, is this a motorcycle? Then, when a new vehicle rolls in, you show it to all 3. Each one spits out a probability. The car model might say 95%, the truck model says 3%, the motorcycle model says 2%. And you just pick the winner. The one that's screaming its yes the loudest gets the final say. It's so simple, but it works incredibly well. And that really brings us full circle. It's pretty incredible when you stop and think about it. This one simple, elegant idea, the S-curve, is the quiet engine running behind everything, from our email spam filters to life-saving medical diagnostic tools. And it really makes you wonder, doesn't it? What other huge, complex problems out there are being cracked right now, not with some impossibly complicated magic trick, but just by finding and combining simple, beautiful ideas like this one?